Hello everyone. Hello. Yes. Hello everyone. Good evening. Uh, Let me just. So net is okay. Let me just present my screen. So and uh, yes, this one is here. Okay, so let me just see whether it is present. So my screen, entire screen, and this is the share. So Riddhi, my screen is visible, right? Can you just confirm it? Whether the screen is visible, I'm in presentation mode. You can just point it out in the comment or something. Okay. Hmm. Maybe this color. Okay. So today we will be discussing the third week of the course, an introduction to cardiovascular fluid mechanics. And so far, uh, uh, like starting from the basics of fluid mechanics and then solid mechanics, there was the discussion about this viscoelastic properties, different components of blood, and like different components of blood. uh, in this particular week, we all started with the viscoelasticity associated with the blood and what the viscoelasticity is and why blood is considered to be both viscoelastic, like having the property of viscoelastic material. So I will be coming to wait. Somebody haven't came. Just let everybody join. Yeah, admit. Yes, two people are there. So I will be once going through the content that has been taught. Like I will be summarizing the things that was there explained in this particular week, and then we will go for some questions related to the week content. And let me just give some time. I will be coming to the same. I hope I am audible. Just somebody confirm my screen is in presentation mode. You can see the screen, right? Hello. And you can write in the comments also. No problem. So this particular week started with the viscoelasticity, and in the viscoelasticity section, let just again somebody came. So they are coming. So we will be waiting a bit, 2 or 3 minutes. Let everybody join. Yes. It is mute.
Available.
So let's. So in this particular week, like elasticity discussion started, and then you went for this Weisenberg effect. So in the Weisenberg effect, what actually happens that this viscoelastic material behaves very differently as compared to the Newtonian fluid. And then you saw that this for the case of Newtonian fluid. So I will be just putting the same slides here so that it will be okay. So my screen is visible, right? Can somebody confirm? Vicky, you can you confirm please the screen is visible? Yes, yes. Okay. So let me see how many are there. Yes. So we were here. So this in this particular lecture, the Weisenberg effect you have been taught about, and then there you saw that when the rod rotates in a viscoelastic fluid, there is some different behavior. What the behavior is, like in this case, you saw that uh, uh, okay, if the Newtonian fluid is there and a rod rotates, then you saw that the fluid goes away from the rod, and there will be the groove formation near the rod or surrounding the rod. But in the case of viscoelastic fluid, you saw that there is this climbing phenomena which is taking place for the given system. So if you want to visualize this system, uh, I will be showing videos for the same in few minutes. But till then, we will be just covering up the what the things are. Like another effect that was explained was the Dicewell effect. In the Dicewell effect, you observe that maybe wait, yes. So can somebody just speak something? I just want to understand whether I am audible or not. Like nobody is responding. Okay. So in this case, you saw that when Newtonian fluid actually drops from a pore, then you saw that there will be the formation of the jet, and that jet, if the velocity increases, the diameter of the jet decreases, and eventually that is a bit constant. But with this polymer that is here, or something which is viscoelastic in nature, with that there will be this effect which is called Dicewell effect, where there will be a kind of swelling or the enhancement or increase in the diameter near the pore region. So this we will be looking at a video for that. And there is something called memory effect, and we will be coming to this about like how this memory effect is important, and it becomes very much important for the viscoelastic material, because there is something called the relaxation time, which actually defines and for any viscoelastic material, the relaxation time is not just a specific number, rather it is a spectrum of relaxation time. Okay. So then then there was the introduction of the Deborah number, and the Deborah number is well explained through this particular proverb, where this relaxation time and the time of observation has been compared together, and then some insights about the Weisenberg number. And then this diaspot model came into the picture, which is this Maxwell's model for this spring diaspot model. And why this model is very useful in order to define the viscoelastic material. So there are few YouTube videos which we will be going to visualize, like whatever was content was there in the course for this particular week. We will be looking at some experimental investigation for the same, so that things become clear, and then we will be going for some of the quizzes related to the content or the three lectures that was the part of third week for the course, an introduction to cardiovascular fluid mechanics. And then we will be coming back. So this is this let me just change the color. Yes, I have to change the color, right? So which color? I can take this one, right? So whether thickness, yes. So and week So this will not be visible. Where is white? If I can add white. Okay, so this is week 33 and introduction to cardiovascular fluid mechanics, right? So the content that I am just going to show you is about this. Let me just add it if it works. Yes. So I have just saved that. So this is this. So we should acknowledge this particular. This is this swell model. So I hope this is visible, right? Yes. So let's see what actually happens. So this is from ETS Zurich, and we will be acknowledging the same. So this particular video you see, what is actually happening is this, the extrude, let us move it this side, yes. So what actually happens, the extrude swells the large viscoelastic stress in the fluid, remembers. So which is the remembering phenomena which takes place in the viscoelastic material, and the deformation of the fluid as it flows from the syringe into the air, that happens. So if you see, the right one is the honey and the left one is the viscoelastic material, and you can easily see that there is the swelling which is happening for this left part, which is the viscoelastic. Though here the honey is considered to be Newtonian, but in this case both the viscoelastic material is there. You can see there is a difference in volumetric flow rate with which these two materials are being flown. So if the change in the volumetric flow rate is there, you can see how the difference is coming dictated by the diameter of the nozzle. Okay, so in this case, as you saw, the honey was the Newtonian fluid, and the solution of PVA and the borax with the food coloring was the non-Newtonian part that they have considered. So which was the viscoelastic thing. Okay, so this video actually confirms the the main thing that we were talking about was this. Where is this? Yes, this swelling effect, which is actually taking place near the nozzle, right? And this, you see this nozzle, which was this dye swell effect. Here, this swelling was happening, which is the increase in the diameter of the liquid stream after exiting from the dye, and it caused by the relaxation of the extended polymer coils, right? So because of that, there is this swelling happening in the case of viscoelastic material, and this can be explained with the help of memory effect. Because why? Because when you saw in that video, there was this 5 ml per minute, and this side there was this 20 ml per minute, and you saw that for the 20 ml per minute, the same material had the larger diameter, the larger ejaculation diameter, which comes because of the memory effect. Because these viscoelastic material, when a shear stress or disturbance is applied to them, they store the energy and they dissipate that with time, and they tries to come back to the initial situation, but they are not purely elastic, so they will never come back to the initial situation. Rather, they will come back to some intermittent position. So for that, they have tried to explain through the this what we were talking about was dye model. Okay, so in the case of dye model, you saw there was the two parallel and the series one, right? So this was the series, and the another one was the parallel one, right? So that, if we see, is the one, let me just take it that side. Is it the same? No. If I can increase it. Yes. So that particular, so this is the basics. So yeah, this is about the models. So this will definitely help you. Let's see, freeze it. Okay. And till then we will be looking at this. Yes. So this is ready, right? So in this one, you see, this is basics of viscoelastic and how the model of viscoelastic material happens. And here this is from non-linear engineering, and here we can easily see what is the two models and how the viscoelastic models are being modeled, right? So if we see, if somebody texted something, let me see. Yes, someone want to join. Let me just take them here. Admit. See them. Oh, yes, they are there. Okay, so what I expect now, this should work. Some net issue is there or not?
We all know what is elastic material.
So
elastic material can be represented by a spring, and it obeys Hooke's law. So this is the simplest form of Hooke's law,
follows the Hooke's
stress is directly proportional to strain.
model, right?
What this means is,
And
if we apply a load
what
on
this
elastic
means,
material,
when you apply
then
the
as
load
we
in
apply a
elastic
load,
material,
there will be some instantaneous
there will be
deformation.
some instantaneous
As long as
right?
we keep that applied load,
And
the deformation will be also constant.
okay.
And
So
when
you
we remove
kept
that
applied
load,
load, deformation
all of
was
the
constant,
deformation
and
will
then
be recovered back.
it relaxed back.
Which means elastic material retain their original shape once load is removed.
So when the elastic
And
material,
on the other hand,
you see
what is viscous
this
material?
regaining
So viscous
behavior
material
is there.
obeys
So
this
for the
law,
viscous
where
behavior
stress
this
is directly
Newton's law of
proportional to
viscosity,
strain rate, not strain. And
So
viscous
for that
material
case,
can be
for the
represented using a
viscoelastic
dashpot.
model,
And when we apply
it
a
can
load
be
over here,
explained
what
through
will
the
happen is,
dashpot,
as long as load is
for the viscous
applied,
one.
the deformation will keep on increasing.
So
And when we remove the load, then whatever deformation occurred, that will be permanent.
So the deformation keep on increasing, and if you remove the load, this deformation is now normal, and it is permanently deforming. But in the case of elastic model, it was like it came back to the initial situation after some time. And as you see this, next, then when you combine these two models, elastic model and viscous model together, in order to explain the viscoelastic material, so new model comes up where which is called as Maxwell fluid model, where this spring and dashboard model both are there. And you see that when the load is applied, there is increase in the stress, and also there is a increment in the spring strain, right? After some time, when you leave, there will be this behavior you are taking place. But what actually happens, you see that there is a permanent deformation because of the viscous part, but there is not it is not coming back to the same situation like in the elastic one, right? So similarly, there is another model where the parallel combination of the two, spring and the dash, was considered, and you saw that here the similar phenomena will be coming up, though the graph is a bit different, but a similar kind of models can be framed for the viscoelastic material. So this was the one that was more important in context of all materials. So other more complicated models can be built by different combination of the spring and the dashpot model, right? So this was the one that we were talking about, is this about the spring and the dashpot model. So about this also we will be going through in detail through some like this was more or less explained very well in the class, right? So here you saw that you had this sinusoidal oscillations, and you have considered the oscillation to be in the form of exponential, which is explained in terms of uh, complexity. So in the viscoelastic behavior of the blood, we saw that this the blood behaves as viscoelastic, and this behavior of the blood to be like, so far before this lecture, we always assume that the flow is steady, but in reality, blood rheological measurement, whatever is to be done, that is not steady. Rather, that is unsteady and pulsatile in nature. Okay, so cardiovascular system is pulsatile and unsteady in nature. So this time-dependent rheological behavior of the blood need to be considered in order to actually get the real picture of the real picture of the thing that is happening. So blood, why the blood behaves as an viscoelastic material. So this viscoelasticity in the blood comes from the two main things. First is this RBC and WBC. This RBC and WBC, these are red blood cells and white blood cells. They are viscoelastic materials. So they deformed. They are having while their motion in the blood, they actually change their shape somewhat. There is this you saw in the case of WBC, there was this the rolling up the wall effect. So there is some evidence that plasma, so as we know, this plasma is nothing but the combination of proteins and peptides. So these protein and peptide chains are present in the plasma. So because of that, there are some literature which is coming up that they are showing that this viscoelastic a little viscoelasticity is associated with the plasma also, and this behavior depends upon the amplitude of the oscillations here and the hematocrit value, which actually shows that how much the RBC is there in the blood. As we know that 50% of the blood is actually the RBC. And then there is this, and also the wall is fluctuating. The deformability is associated with the wall also. So together everything adds up to give a property for the blood. The viscoelasticity comes from the its constituents, right? So as through this we this it has been explained that this complex viscosity for the blood, how it is changing. So there is two parts. There is this elastic part, and there is this viscous part, and this steady state viscosity approaches viscosity component at high. So and there is this steady state viscosity. So there was this decrease, which is similar to the other fluids like this pseudoplastics, which has been observed for the blood. Okay, but there was some different behavior. So normal stress differences, and then relaxation time, simple spring dashpot model, oscillatory shear motion, and the blood rheology under oscillatory shear. So these five things were explained in this particular lecture. So another explanation that is left is the one this one, I think. Yes. So here this Weisenberg effect. So what is this Weisenberg effect? And a very beautiful video from the Christopher actually explained it. And this particular video, if you see this, the Weisenberg effect is what? As studied by this, we should acknowledge them. When a fluid undergoes a stress, a certain amount of strain or deformation is observed, right? And because of that, the relationship can be viewed on a stress-strain form. So this is for the Newtonian shear. So like every fluid, Newtonian, non-Newtonian, we observe that this is the standard: dilatant, Bingham, plastic, Newtonian, pseudo, Bingham, pseudo. The derivative of this stress-strain curve can be used to define the viscosity of the fluid for the specific shear, right? So viscosity has been calculated like this for the fluid. And then when you see this, so let me just explain this particular graph a bit more. If you see this, uh, so here viscosity is almost constant for the Newtonian fluid. So because with the shear rate there is no change in the viscosity of the fluid, but this is not true for the non-Newtonian fluid. As in the non-Newtonian fluid, this viscosity can increase or can decrease or can abruptly decrease because of the applied shear rate. So in case of pseudoplastic, this decreases. So like in the case of blood we saw just before, there was the decrease in the viscosity with the shear rate, right? But in the dilatant, the opposite is there. The viscosity increases with increase in the shear rate. So if you see this very carefully, a Newtonian fluid, water or oil, the viscosity does not change depend on the stress applied, right? And that is this yellow part in the main viscosity versus shear rate curve. When the rotation stress is applied to one of these fluid, inertia and the gravity dominate, forcing it out of the fluid. So you see what actually happens. In the Newtonian case, all the fluid is going outside and deep is coming up in the middle side. However, the fluid known as pseudoplastic or the non-Newtonian fluid like the blood decrease viscosity with the increasing stresses. So this is this yellow part which I was talking, that viscosity actually decreases with the shear rate, and then this applying the rotational stress decreases its viscosity near the rod, and this difference causes a force that overcomes inertia and this. So you see there is the climbing effect which is taking place near the rod or the rotational thing. And why this actually happens, this can be lead to the interesting phenomena, that is the Weisenberg effect that we were talking about, right? So this Weisenberg effect you saw. So you just look at this is from the MIT's non-Newtonian fluid lab. And then the pseudoplastic contain polymer chain that can stretch and flex and even bend under the stress. And near the rod where the stress is highest, the chain orient themselves in the direction of the shearing. And because of that, the chain near the wall therefore are stressed more than those near the rotor, and creating a higher state of the energy near the wall. Because of that, the chain conglomerates in an area of the lower energy where the stress is highly near the rod. So we saw that this particular scheme, non-Newtonian, there was the deepening near the rod. In the polymeric solution, which in the where the climbing of phenomena is happening, and we can see that from the top how it looks, this radially outflow and radial inflow is happening near the wall. Because of that, the overall this conglomeration pushes the fluid in only direction it can go is the upward in this case, and this kind of circulation forms into the picture. So this is another viscoelastic fluid where this can be seen, and fluid with the more elasticity had larger difference in the length of the stress, and you can see this the climbing phenomenon. So this is another climbing phenomena. You can see sometimes this climbing phenomena has been used as an application for the footing, but in this case we can see this pseudoplastic fluid also exhibit a few other interesting characteristics, the case effect. So this effect we also saw. So if you see what it actually happens, this is the same that we were talking about. From the nozzle, there is this memory associated with that, and because of that, there is this increment in this diameter. So die-swell effect, this is the one that we were talking about. Here the swelling is happening, right? And you can see this. This is happening because of this. If the viscosity increases, you see this diameter is okay. So this was some experimental videos that I wanted to show you, so that the complete picture comes into the frame and it completes up. Like during the classes there was the discussion, but the real experimental pictures will actually add up more, right? So let me add, yes, add it. So now we will be looking at some questions before we actually go for some other concept that was there. So the first question that I want you to look at is this one. So the I will be writing the question anyway. So the question one is okay. So this question one is uh, in an oscillatory flow. Okay, in an oscillatory flow, oscillatory flow, right? When the Wormersley number, when the Wormersley number increases, which of the following increases significantly? Which of the following increases significantly? Okay, so this is from the third lecture of this particular week, where you have been taught about the flow profile calculation for the uh, uh, blood vessel kind of for the blood vessel kind of geometry, where this Wormersley number came into the picture after the some generalization and assumption in the Navier-Stokes in the radial coordinate, where you got that when this and you solve it for three limits. First was this very low Wormersley number, second was the very high Wormersley number, and third was the intermediate Wormersley number. And there was some physical interpretation about the same, as well as the how sinusoidal characteristic of the pressure gradient and the velocity. So I am telling two things. First is this pressure gradient and the velocity, how this two thing have been related to uh, with the temporal variation with the sinusoidal fluctuation of these two parameters, uh, which has been done by using Fourier transform, where this periodicity has been taken care through this exponential term e I omega t, so which was e I omega t. So you consider that del p by del x to be del p by del x e I omega t cap e I omega t. So through that you solved the entire Navier-Stokes for that under some assumptions, and you come up with some velocity profile for the for this flow happening through the vessel, right? So in this one, the option A is uh, viscous effect, viscous effect, right? Option B is what? Frequency dependent inertial effect, right? Frequency dependent inertial effect. Option C is what? Flow turbulence, right? And option D is static pressure, right? Static pressure. So you just solve this and comment your answer in the comment box. So this is this in a oscillatory flow. So the last lecture was entirely dependent on the oscillatory flow, which is actually an actual case in our blood vessels, where this pressure is a function of time. So you saw the lecture started with the curve P versus T, where the pressure was actually fluctuating, and that fluctuation was very there was not periodicity associated, though in our analysis we are actually considering somewhat sinusoidal periodicity but it is more complex actually. Yeah, though this model actually gives some physical insight to the phenomena which is taking place. So, so the option A is viscous effect, option B is frequency dependent inertia effect, option C is slow turbulence, and option D is static pressure, right? So you look at this. Okay. So, so if somebody replied, let me see. You can reply whatever option you feel is correct. We will be solving some other questions too, along with these. Some expression based question, the functions that has been used, we will be getting those in a minute. Flow turbulence. Yes, Srilata attempted flow turbulence. So option she is thinking that the option which option is that? Let me just open. Yes. Okay, C. You are saying C. Somebody else? Somebody else? So option C attempted, somebody else attempted. Option B, yes, option B, somebody attempted. Okay, let me just come to my screen. Okay, so the answer to this I will be saying, and then I will be saying why this option uh, turbulence one is not actually associated. Like option B is the correct answer. So correct answer is the option B. We will be looking at why option B is correct in a while. So option B is correct, right? And why so? We will be looking at that, right? So as we know the Wormersley number, so if we write this Wormersley number to be this Wormersley number, okay, alpha is what? Alpha equals to R under root of omega divided by nu, right? And then this R is what? R is what characteristic length, okay? R is what characteristic length of the vessel, like vessel radius in a biofluidic fluid mechanics. Okay, and then omega is what angular frequency of oscillation with which this angular frequency of angular frequency of oscillation, and alpha is the Wormsel number, and then this nu is the kinematic viscosity, right? This This is kinematic viscosity. So this is V by rho. This kinematic viscosity. Okay. So if you see this, let me just take the white color again. In this one, what actually happens is with the second option is this. Why this term is actually explains everything. It's a this term is suggests that the frequency of omega increases, so the Wormersley number. So if omega increases, the alpha increases. So it means that, and in the high alpha flows, uh, fluid near the wall lags behind the pressure oscillations, while the core region moves with the less resistance. So as you saw in the main picture, uh, so the fluid near the wall lags behind the pressure, right? Uh, and then oscillation happens while the core region moves with the less resistance, and this resistance is more plug-like. Okay, and this velocity profile where this velocity gradient near the walls become steeper is the one reason where this effect of inertia is actually coming into picture, right? So if we will be looking at like the for the low Wormersley number situation, you had this uh, uh, a velocity profile which was actually coming up and which was actually reversing its direction. Like there was this backflow coming up into the picture, and so because of this reason, this option B is correct one. And as the turbulence, one somebody suggested, the turbulence, like uh, the high alpha doesn't mean turbulence by itself. High alpha mainly cause strong inertial effect. Phase lag in the velocity happens and the plug like flow happens, right? There will be like this flow is happening, and the net velocity is coming up like this velocity profile. The velocity profile is not like parabolic like this, and this turbulence needs high Reynolds number. Means there has to be strong instabilities, which Wormersley number does not guarantees. Okay, so for turbulence, there should be strong instabilities, flow instabilities. So there are various hydrodynamic flow instabilities like this because of the flow there is KH instabilities, Kelvin Helmholtz instabilities, and then this Rayleigh-Taylor instabilities, and then there is this Stackman-Taylor instabilities because of the viscosity gradient. And because of those like there are various hydrodynamic instabilities, and those instabilities, if it happens at very high this RE Reynolds number situation, there is this random currents forming, and because of that irregular flow, random flow, chaotic flow, the turbulence comes into the picture, which is actually not that high alpha comes up into the high inertial regime, which inertia is coming up from the angular oscillation frequency. Okay, it is not the case where this Reynolds number is very high. Okay, so this when can high alpha contribute to the turbulence? So there could be some possibilities, but which is not actually coming up into this picture. So turbulence requires sustained disturbances. Okay, so when alpha causes velocity phase lag and thin, there is lag in the velocity. Let me just come up to the slide where this was explained, like lecture 10, I think. Let's see this in the slides you may have saw. So Murray's law was there in the lecture, is central week of this particular week. So there this cost minimization was there in terms of minimizing the radius of the blood vessel, and the explanations about flow bifurcation, we will be coming into the picture. So this pulsatile, I was talking about this. So this gradient of the pressure actually depends on the time, and this time dependence is actually shown here, and this is periodic in nature. Okay, and then this we have done through the Fourier series in terms of sine and cosine. After applying the conservation equations, we got the main equation in the r and the z direction, and after non-dimensionalization of the same, we raised to the main equation, which for that we solved for various situation of high alpha, low alpha, and the intermediate alpha, right? So this term, you can see that, like, when you are saying that Vomersley number is high, that actually comes up with the omega is high. Okay, and then this we see here, this Vomersley number is what? Inertia force, oscillatory inertia force to the viscous force, right? And it is high when the viscous forces are low. So in that case, Reynolds number will also be high, but oscillatory behavior will be there. So this oscillatory behavior is the one which is actually leading to the Vomersley number to be high or low. And in that case, there is this oscillatory boundary layer creation, and then this oscillatory boundary layer condition definitely thickness definitely depends on the frequency with which the oscillation is happening. So that's what I want to say. And the next question that is there is the one. Let's solve this. Yes, the next question is question number 2. This question says, under which situation the obtained velocity profile okay, let me just correct it, profile for oscillatory motion is similar to Hager-Boselli equation. Option A is alpha very high. Option B is alpha very low. Alpha is the Vomersley number, right? This is Vomersley number. Option B is very low alpha. Option C is intermediate alpha. And option D is none of these. Okay, so this is the question. Just look at this. An attempt. Under which situation the obtained velocity profile for the oscillatory motion, like you had na, the derivation of the oscillatory motion, like and there we got the introduction of Vomersley number and everything. There we considered the pulsatile flow to be this this temporal variation of this pressure gradient and the velocity. Okay, so harmonic solution was there. So in this case, when you solve this for small alpha, for large alpha, in that case we will be discussing the graphs also, so which was similar to the main thing. Okay, So you just attempt it. The question is here. Let me see if somebody replied. You just attempt it and give your answers in the comment box. Meanwhile, I will be joining. Okay. Okay, so let's get back to the job. So somebody attempted, right? Yes, B. Somebody attempted B. Let's see. Sri Lata attempted B. Alpha is high. Alpha is low. So yes, in the case of alpha low, the solution is a bit similar to this Pausely's equation, right? So this one is right answer, and let us see come to the solution of the same. Let's see this. Okay, this one is like B is correct answer. So B is the correct answer. B is correct option. Right. Alpha low. So why alpha low? Like you saw, let's see it is here or not. Let us see. Like you saw in the case of alpha low, the final velocity profile, what is what? The final velocity profile look like the Vz, which was there, is minus 1 upon 4 mu del P cap divided by del Z, and this is a square minus r square e to the power I omega t. So in this one, this if you take a common, this comes out to be r by r, and this is somewhat similar to the and also there is two things which comes into the picture, and the in that case u equals to u max. 1 minus r by r whole square, so it comes out to be r square minus r square divided by r square, right? Like this you get, and also this Pausely equation Hagen-Poiseuille equation, and then this is this alpha low Raumer-Moseley solution. Alpha low Raumer-Moseley solution. In the both case, you see this. If you take this this R this side, similar solution coming. Just this term is coming up new in the case of this, because we are considering this to be oscillatory consideration, and you are actually solving it in the unsteady state condition where you are actually considering the time term, and also this in alpha low. So what does that alpha low implies? You understand that alpha by r equals to what? Under root of omega divided by nu, right? I'm talking about this Wormersley one. So in the Wormersley, we saw that this the main explanation about this Wormersley number was under two situations. For the high alpha and for the low alpha, we had this. So this alpha you had physical significance was what? Was what? Oscillatory inertia force to the viscous force, right? Viscous force, and this is again in another term when you solve this you had to be this alpha square equals to what? Omega square, right? Alpha square was omega a square by nu, right? And then this is what? From here you had alpha equals to what? A divided by this nu divided by omega to the power 0.5. It is under root anyway. So it gives this tube radius, right? Tube radius divided by what? The oscillatory boundary layer thickness. Oscillatory boundary layer thickness. Okay, so in that case, this for the low alpha, this low alpha means that these viscous effects are very high, and when viscous effects are very high, it means this the main expression that was there for which the entire solution is being calculated was the main. If I write that expression too, is the this one where this alpha square del Vz star divided by del T star goes to minus of Reynolds number del P by del Z, right, plus 1 by R. These were all scaled one, del by del R, okay, R star del Vz star divided by del R star. Okay, so this is the one, right? And here if you see that when you are having this high when you are having this alpha to be low, in that case alpha low means high viscosity. High viscosity means you are actually considering this term, which is actually the viscous dissipation term, and the same viscous dissipation term valence was considered when we derived the Hagen-Poiseuille, and we got the relation of Heisenberg equation, that is delta P equals to 3 mu VBL, delta P equals to 32 mu VL divided by 2 GT, right? Rho GT. So you these were so this in terms of Q, right? Let me just see. In terms of Q, if you write the same and you will get that is also for the laminar case, right? The laminar flow situation, and for the case of laminar flow situation, if you see this laminar flow situation, the consideration of I mean this laminar flow, this solution of delta P you got. Let me just write. This one was, I think, in terms of Q, if you write it, let me just write it in terms of Q. So this comes out to be delta P equals to 8 mu L. So if you expand Q, uh, and there will be aerial term coming up and Q converts into the velocity. So because of that, this, and Q is actually what? Q is actually what? Velocity, meter cube per, this is what? Meter cube per second, unit time. So you have to multiply it with area, and area you will take as pi r square. So this you resubstitute, then we will get it in terms of velocity. Okay, so this is it. The next question that is there is, which of the following is correct? Solution of, which of the following is correct solution of, let me just write question. Which of the following profiles are correct solution of what? I will be just taking the differential equation that we just wrote of, let me just take it completely. The same equation I will be dictating of, let me just write following differential equation, right? Following differential equation. So the options are, let's write option A is what? Just say, so this is actually taking care of, this question is related to this, our third class of this particular week, and where you have been taught about this oscillatory, under in the case of oscillatory motion, and inside the pipe or tubing, which is similar to the one that we are considering. So which of the following profile or expression slash expression we can write profile slash relation is correct, right? So the option A is what? Option A is, let's draw it, whether the things are online or not. Yes, we are online. So it is R by mu delta P divided by delta Z equals to del 2 by del R2 Vz. Okay. B is R by mu del P by del Z equals to del by del R, R del B R by del R. Okay. So which of the following is correct? The next is C is what? C is Vz equals to minus 1 by 4 mu del P by del Z cap A square minus R square e to the power I omega t, right? And option Option D is, you look at the options, right? So which of the following is correct for the given differential equation? And option D is what? So we have to a bit zoom it down, right? So option D is, let us take this. So Wz equals to -1 divided by I rho omega. Okay, so let us solve it a bit more. If you write I divided by rho omega del p cap by del z. Okay, so which of the following is correct? So if I can zoom it down, it happens. Yes, we can zoom it down. So which of the following is correct? So you attempt it. Okay. Which of the following profile or relation are correct? So profile means the velocity profiles which are there, and the relation means some equation that actually dictates some physical force term, which is actually a part of the Navier-Stokes with which the entire discussion is started, right? So if you see this, so please attempt. So similar kind of questions will be there. The questions will be in the final exams, also in the assignments. In this week assignment, maybe you have got the assignment. The questions are a bit tricky. At the same time, they are the part of the contents which is being delivered to you. Either the content is being delivered from the instructor side or the content that I am delivering. Around these weekly sessions are just for the revision. At the same time, we will be discussing some questions which will be related to the content which has been taught in the particular week. And again, this contents are actually helping you in order to solve the assignment and some of your queries which you may have built up during the course of going through the lecture for the week. And this, if you see, let me just put the screen over here. Where is this? So this was the question. So which of the following profile are correct? You just look at this. We can adjust the page size, this to be A4, not A4. A4 landscape, how it comes. Oh, it is here. Okay, if I can change the color. Oh, so if I, it's very difficult now. Okay, so you see this. So this is from the last lecture, the last week, last lecture. So this pressure and the flow in the circulatory system that has been solved. Okay, and you got that this like this in this one cardiovascular system is the pulsatile. We have in this an average in a healthy human, we had this 72 times per minute it beats. Okay, so whatever processes or the flow processes or the circulatory processes that repeats itself about one per second, because the 72 times per minute almost this is close to the 60 second. Okay, the frequency is about 1 second, right? So the flow is not steady, it is assumed in the Pausily flow. Okay, so, though the positive flow situation was also not correct for the situation which is happening in our body, as we saw that rather it is the pressure gradient or the pressure that drives the flow in a circulatory system, and that changes almost every second. So, it is the function of time. That's why this delta p and the delta and v velocity both have been taken to be the periodic function uh, in order to take care of the take care of its pulsatile nature. So you saw uh, and if you look at this, so if somebody attempted, let me just see. No, nobody tried, so I will be explaining it. So if you see this, this is the same solution that we had for the low. If somebody C, yes, C is there. Sri Lata attempted C. Okay, so ma'am, let me just see if it is correct. So C, right? So option C is correct. Yes, option C is correct anyway. Velocity profile will be same as the same velocity profile we got. So in this case, if you remember, how was the picture coming up? If you see that in terms of this flow visualization. So if you remember, like I can take this image also that side, because in order to fully understand that, this will be helpful. Okay, so let me just take it, then I will explain it. Okay, so if you see this, so in this one you see this is the solution of the same, and the delta p is actually changing with the time, grade of p. So when the pressure gradient is low, in that case, from here if you see, when the pressure gradient is low, okay, so in that case also there is this flow and if the pressure gradient is low, there is this forward flow and the velocity profile is parabolic, and if the pressure gradient is very high, in that case entire flow reverses itself and there is the flow reversal which is taking place. And then this actually helps to see that how the pulsatile nature of the flow is happening. Okay, so this actually helps you in order to see the main thing in this picture. So if you see this Vz equals to minus 1 by 4 mu del P dash by del Z. So in this case, this a square minus r square e to the power I omega t, this time and the spatial, both things are considered, right? Okay. So option C is correct, definitely. And while deriving this particular term, you may have seen uh, this was the step which came before. You just generalized it in terms of this different alpha high, alpha low, and in the case of alpha low, low Wormsley number, this particular the term comes into the picture. So this is also correct. Okay, this is also the correct. Okay, so this is no. If I can change it, yes, this pen I have to change, right? Okay, this is correct. So this option is correct and this option is correct. And this particular option also will be correct because in the case of high, alpha high, you get the profile to be dependent on this delta P, right? Okay, let me just set it. I will be just you look at the question and observe it till I will be just getting. हाँ हेलो भैया भैया क्लास क्लास है मेरा थोड़ा बात करते हैं ना वो 9 बजे खत्म होगा इसलिए वो साइलेंट फोन हुआ था हाँ yes so you may have gone through this this I will be coming to the wait the lecture itself. Let me just see. Yes, this is here. Asymptotic solution, small alpha, right? So in this case, for the small alpha, you saw that this particular expression came into the picture, right? This one, which was the option B, if you see. Let us see this. Yes, this was the option B. We just take it this side. Yes. If you remember this, del by del R or del V Z. No, even the option C is not correct, right? Because we wrote it here R. This is not correct, right? And this is not correct. So this is also not correct because we wrote here VR. If it is VZ, then it is correct, right? And you just look at this and till we will be coming just I am just opening the expression. Yes, let me just see. Yeah, this. So this particular derivation was the intermediate part. Okay, intermediate part of this. So this was this, and then this particular steps. हेलो नंदा अरे टीए है मेरा वो थोड़ा 9 बजे खाली होंगे बात करते हैं ना ठीक है 9 बजे के बाद कॉल कर हाँ ओके सो व्हाट इज let me just see. Oh my god it is oh, sorry this was mute wait yes so you saw this is the solution of the same for the small alpha and you got the expression and that was the intermediate and for the large alpha when the alpha value is very high we will get the solution to be this one. Let me just fix it here. So the for the high alpha this vz comes out to be I rho rho omega del p by del z. So this is for the large alpha value where this viscous dissipation terms actually diminishes and the flow velocity is balanced by the pressure grad, right? And because of that, this Vz equals to del P cap by del Z, right? Okay, so now It is correct. And yes. So this was the, let me just discuss the same profile also, because this is very important. Where is this? Yes, this one. So in the case of large Wormsley number, where the velocity profile is Vz equals to directly proportional to the pressure grad, you see that this like the pressure grad like the velocity profile is coming to be constant, and it is like plug flow. So though the flow reversal will be anyway taking place because of the I omega like the temporal part which is coming up into the picture, but this thing is there, right? So let's come to the next problem. What I expect. So if somebody is there, yes. So the next question we are going to solve now. So the next question is. Uh, yes, the next question is now, let me just write the next question. Which of the field is Wormsley number most commonly used? Question number 5. Question. In which field? It is very straightforward question. Field is the Wormsley number most commonly used. Right. So A is chemical reaction kinetics. Chemical reaction kinetics. B option is what? Biofluid mechanics. C option is what? Heat transfer in solid. And D option is what? Aerodynamics of high-speed aircrafts. High-speed aircrafts. Okay, so this is the question that I want you to attempt, right? And you just attempt it. So if I can increase the size, so if somebody attempted, let me just see. We'll be looking at. Yes. So Vicky saying B option is correct. So let us see. Biofluid. Yes, biofluid dynamics, chemical reaction kinetics, right? So B option is correct, right? Because our situation that we are actually the course title itself says this is correct, which is biofluid, which is biofluid mechanics, where the actual so whatever flow which is happening in our blood vessels, those are what? Those are actually coming into the category of what? So this is, suppose this is the blood vessel. Okay, so here you are having this flow of plasma, right? Then there's WBC, RBC, platelets, and in the plasma itself there are lots of proteins, amino acids, everything is there. And these proteins and amino acids are one of the reason for viscoelastic property, apart from these viscoelastic cells. which is there. Okay. So because of that, this is the biofluidic mechanics, right? And now, so this question, if you attempt, this one is good question, a bit tricky one. And if you see, for blood flow in small capillaries, for blood flow in small capillaries is right. Vicky, can you just mute? Okay, thank you. Small capillaries, the blood flow in small capillaries, the Wormersley number is generally is what? Very high. Very high. In brackets, alpha is greater than 1. Okay. B moderate. Alpha is approximately 1. And C very low. And D is what? Undefined. Okay. It is not defined, right? Commercial number is not defined for small vessels. It says that. So you look at this problem and try to answer the following. Everyone, please look at the problem. I think we had enough questions on third lecture, so we will be now taking questions on first or second lectures of the week. So we have to actually revisit the entire content in this particular lecture and have some of the questions. Through that questions, I will make you remember few of the important concepts that will be anyway maybe asked in the assignments, and at the same time that can be asked in the form of question in your examinations, final examinations, right? So you just attempt it. Anyone, please? You just attempt it. So you Vicky is saying C, right? 830. Vicky is saying C is correct, which is very low, means alpha is less than 1, which is laminar case, right? Yes, Vicky? Yes, this one is correct one, Vicky. You are correct. Because this he actually predicted it, like flow in a capillary. So what is the typical diameter of the capillaries that you remember from the first lecture that was there? The typical diameter of any capillary. So the what is like you are having the like this bifurcation is bifurcations in your blood vessels, right? So right from the artery to the veins, you will be having lots of different dimensions bifurcation. So it is in mm, suppose this is in 1 mm, 0.5 mm say, then there will be something like 40 to 80 micron. These are called like arteries, arterioles, and these are also having some bifurcation here. And then you will have something called capillaries here, and these capillaries are like what? There will be these flow features which is coming up into the pictures. You see this one. Okay, so these are some flow features. Because of that, these are capillaries, and the typical diameter of these capillaries are what? Like 8 to 2 to 8 micrometer, right? Or 5 to 10 micrometers, suppose. So these are very small. So anything in very small microfluidic channel, if you see, if a channel is there and the diameter of these channels are very small, right? Uh, Suppose in this case we are saying 5 to 10 micrometer, right? So if the diameter is very small, the channel will be actually having this lots of one effect. So this is so confined, very confined, right? Very confined, right? Uh, Diameter is very small, right? Very small. So in these cases, this comes into the microfluidic domain, microfluidic domain, where this surface effect will be there. So definitely they will be there, but in this case, the flow is assumed to be laminar. So necessary is there will be lots of wall effects. So there will be this complete velocity gradient creation, and this viscosity, this velocity which is profile which is being created is because of the 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 viscosity of the net viscosity of the blood, and as a whole, the flow is assumed to be laminar. Okay, mostly in the low diameter tubes to be laminar. So as we remember, in our case, for the laminar situation, where these viscous effects are dominating, where the alpha, so alpha is inversely proportional to us viscous force, and here you have oscillatory, inertial, inertial effect. Okay, so in this case, if you remember this oscillatory inertial effect, alpha equals to oscillatory inertial effect divided by viscous force. And if viscous force is high, then alpha is low. And in the case of this is the ideal situation for laminar flow, which is for which the positive expression was there, and also the laminar flow condition. Wormsley number is generally defined. So in the capillaries, there will be laminar flow, right? And for that, there will be this similar velocity profile like the Hagen positive velocity profile, but it is oscillatory. So there will be this velocity profile which is similar to the velocity profile which was in the case of Wormsley law, which is this one that we already considered. This is the velocity profile which will be coming up for the same, right? So C is the correct answer. So C is the correct answer, right? So in this one we will be going to side. Yeah. So C is the correct answer, right? Okay, so now the next question that we are going to solve is, so let's write in chat what I was writing. Okay, so the next question is, let us see this. Yes, if you can see this in the right. So according to the Moore's law, okay, so we will be going to that.
ఏమనలేదు గేట్ ఉందని అడిగారు ఏం చేయాలి అంటే వద్దు ఇంకేముంది చూడు 4 8 ఉందని అడుగుతున్నాను.
Okay, so we will be taking some question on Moore's law. Okay. Okay, and then so a few questions on the first lecture, which was about the viscoelasticity. Though in the beginning we saw some of the videos on viscoelasticity, some experimental investigation that was actually listed in the literature about the viscoelasticity. Okay, so the first is this question is what does Murray's law describe? Okay, what does Murray's law Murray's law describe, right? So the option is the relationship between viscosity and the vessel stiffness. The relation between fluid viscosity and vessel stiffness, right? Option B is the optimal branching ratio of the blood vessel for minimal energy dissipation, right? The optimal, okay, branching ratio of blood vessel for minimal energy dissipation. You may remember some of the concept that was there in the second lecture of the week. Close to that lecture only, the question is the maximum blood flow velocity in arteries. The maximum blood flow velocity in artery. Okay. And option D is what? The effect of turbulence on microcirculations. The effect of turbulence on microcirculation, right? Okay, so you look at this may help, right? You just solve this question. What does Murray's law describe? The relation between the fluid viscosity and the vessel stiffness, the optimal branching ratio of the blood vessel for minimal energy dissipation, the maximum blood flow velocity in arteries, and the effect of turbulence on microcirculation, right? So you please look at the questions which are here. B, somebody is saying B. Wait. So B, you are saying, right? Someone more, if you want to attempt, you attempt it. Please attempt. The more you attempt, the more you will get some insights about, right? So it's like so you please look at the questions, right? So option B is correct answer, right? Definitely this one is correct answer. And so option B is correct answer. Option B is correct answer, right? As you saw, this was for the branchings. So branch channel, the net, how this, and then you use this concept of minimizing the cost. So there was two costs associated. So let me just discuss the entire thing again to you, so that it reminds of the entire lecture once again. So somebody came. Let me just see. Admit, yes. Okay, so this entire see this Murray's law described this optimal branching ratio of the blood vessel for the minimal energy this dissipation. If you remember, the entire lecture is started. This is somewhat something like plant design and economics. A subject is there in Department of Chemical Engineering. If somebody is from the chemical engineering, and in the chemical engineering there is this plant design and economics, or any a design economics course where you actually try to minimize the cost, right? So the cost minimizes and actually falls up to the to something called this through the Murray's law. They tried to explain it, right? So I can just increase it a bit so that slide is very well visible. Yes. So if you see in this one, if it comes down, yes. So as we saw that there are lots of flow bifurcations which is there in the blood vessels which is inside us, and because of that there will be this uh, uh, change in the velocity from one stream to another. Because there is bifurcation, there is this lots of like uh, from one Q1 there will be distribution of Q1 because of the branching, and then there will be disruption is everything in the shear stress profile, in the gradient of the pressure, and in the velocity, right? So if you actually remember the Murray's law, what is that? It is based on the minimization of the cost function, where the cost function of in this Murray's law has been defined for the blood vessels for which he was actually calculating. It was as the sum of two things. First was the work which is done on the blood for what? For pumping it. So which was Q into delta P. Okay. And the another one was sometimes because of this blood actually have some metabolic rate of its vessel itself for the creation of its vessel. For example, energy per unit time required to renew the blood in the vessel, right? That is pi r square, which is the area into the length. Okay. So the another term they got as the cost function to be q into delta p plus k pi r square into L. And if you see this very carefully, this cost function in this one, the delta P, as in the blood vessel, you will be considering this laminar flow situation for as well as the fully developed flow condition. Okay, so in that case, this cost function where you had this delta P, you replace that delta P to using this Hagen-Poiseuille flow equation, and you finally had this CF to be this one, right? CF to be this one, okay? And then this CF you minimized to get the minimum. You have to minimize this function to get the minimum radius, and you from there you interpreted that this flow rate has to be proportional to some power of radius in order to have the minimum cost, right? So that was the one that we actually discussed, and from there you also calculated the minimum cost which is there, okay, and lots of other things that you actually uh, considered. So there was this beautiful discussion, like through the calculation you got that Mary's law is having some dependence of flow rate to the radius, right? And in the Hagen postulate, you know that it says that radius to the raised to the power 4 is actually the dependence of the flow rate to the radius, right? But in the case of Mary's law, you had exponent to be 1 unit less, right? So that was again explained that through the experimental investigation of another scientist. He said that this through the experimental investigation, he suggested that yes, the Murray's law, whatever he actually explained, was correct in terms of what? In terms of real blood situation, though it is not fully correct, but yeah, it is the closest and somewhat accurate result, which actually gives you some value. So that I will be in a minute showing. So this was the experimental investigation which was there. So through this experimental investigation, he actually compared the Murray's law dependency on the power of R, right? So that was it. Okay, so the next problem that we are going to solve is this one. So let me just write that question. Okay. Okay, so the question is, if the parent vessel, oh no, if the parent vessel radius is 3 mm, if the parent vessel radius is 3 mm and the daughter one daughter vessel is right, and one daughter vessel is 2 mm, right? What should be the approximate radius of second daughter vessel? What should be approximate radius of approximate radius of second daughter vessel, right? What should be radius of second daughter vessel according to the Morris law, right? To Morris law. You just attempt it. This is somewhat numerical problem. So option A is 1 mm, right? Option B is 1.5 mm. Option C is 2 mm. And option D is 2.5 mm. So this is a numerical problem you just attempted. Last option is 2.5, right? Just remember it, right? Okay. Yes. If somebody can, actually you just attempt it, the option is in front of you. Somebody is saying C is the correct answer, which is 2.5 mm. Okay. Or 2 mm, right? Just attempt again. Okay, so yes, the correct answer is the one that he said. It is a bit close to, but not the exact one. So if you solve this particular question, is somebody said the same. Let me just see where the answer was. See, where is this? Here, yes. See, somebody said, right? So let us see the answers. So if you see this, you know that Marisla says what? According to, suppose this is the parent, and this is bifurcated into two dotted streams, which is 1 and 2. This is the parent P, right? So you can write RPQ, so which is QP equals to Q1 plus Q2, right? And from here RPQ equals to R1 cube plus R2 cube, right? And in our case, it is given that Rp equals to 3 mm, right? Our case, it is given, what was the Rp? Okay, 3 mm. And R1, I think R1 was 2 mm. And you need to find R2, right? So if you actually put all the values over here, 3q equals to 2q plus R2 cube, 27 equals to 8 plus R2 cube, and you get R2 equals to under root of cubed root of 19, which is 2.668, right? Okay, so this is the answer. This is mm. So you are correct. So that was this problem. So now the time is very less. Another question that was there. So I will be just explaining you the same. What is the key assumption about the energy minimization in the Murray's law? So there was this three option. So key assumption in the energy minimization is the Murray's law. There was the this uh, assumptions. First is A is the sum of the kinetic and the potential energy is conserved. Second is the power required for the blood flow in minimized by the balancing viscous dissipation and the metabolic cost. Yes, and the C option is the blood vessel always dilates to maximize flow rate, and the fourth is blood flow follows a turbulent regime for efficiency, right? So if you see the question that I am saying, this one, the from the options only you actually see that the power required for the blood flow is minimized by balancing the viscous dissipation and the metabolic cost. Okay, so metabolic cost was the another term, second term, and the viscous dissipation was Q into delta P1. Okay, so that was it for this one. And also, if you see this Murray's law, the main takeaway message from the Murray's law was the Murray's law was this that the flow separation actually depends on this. The flow in through the bifurcations actually depend on this third power of the channel radius, right? And the Murray's law follows the sum of the cube of the channel radius at each generation, for which we have just solved the numerical. So at the bifurcation, the velocity profile is skewed towards the inner wall. So we will be looking at that. So I will be actually explaining theories now so that everything becomes clear to you. And also the secondary flow is also observed after the bifurcation, that also we will be taking care. So secondary flow is actually coming because of the effect, unsteady effect which is taking place after the bifurcation. That is one thing, and at the same time there's the various costs which are being associated with different phenomena which is taking place. So if you see let's take this slide here. If you see very carefully, so let us take this here. Let's, okay, so this one I am saying, I just want to max. Okay, so yes, so the flow behavior at the bifurcation, what actually happens? So the main thing that is there, if you see, if we just expand this side, yes. So if you see this, okay, so the main blood vessel, which is actually this side, is your blood vessel, right? And then this bifurcation is actually taking place, right? If you actually draw it very carefully, you will see that suppose a fluid with the some Q it is coming. So parent vessel is this one, right? And here the main thing is this, the way everything adds up, the angle of the bifurcation and the flow which is coming, the flow is pulsatile in nature because of the pumping of the blood. When it gets divided, what has been observed that this here the profile is like, uh, I mean the profile is like this. It's like maximum velocity is near the wall, which is inside towards the bifurcation, and then it decreases like this, right? This is not the same for entire range of this, as this also fluctuates, the wall also fluctuates. So because of that, there will be change. But yes, typically what happens here, there is the boundary layer formation, and towards the outer wall side, there is the flow separation. So if you see outer wall side like this, and here there will be flow separation, right? And inner wall, there is this boundary layer formation. Okay, so why most of the time you see that the plaques, which is the thrombosis. So what is thrombosis? If you see, so in first week or second week, I have had one video and explained there this blockages which is being forming in our blood vessels. These are actually forming because of this cholesterol buildup, fat buildup, and the plaque which is there. They build up within the inner wall of the blood vessels, and they actually reduce the effective diameter of the blood vessel, right? And because of that reduction in the effective diameter of the blood vessel, there is this fluctuations associated, and also there is this difficulty in the proper pumping of the blood, and the patient feels it difficult to pump their blood. Okay, so if you see what will be happening in the thrombosis, there will be this some kind of this kind of plaques will be forming. So now only this area is available for the blood to flow, right? These area is available, so this is blocked. So this is, and because why this is forming, because mostly through the hematodynamic context, it has been explained that as here there is the flow separation, there is this reduction in the velocity. Through the Murray's law also it has been proved that the sum of these two radius effective area is more than the area of the parent. Okay, so here the flow will be reducing anyway, but towards the outer wall there is the flow separation, and this flow separation is responsible for the formation of the plaque. Okay, and if you see this in detail through this one, if you actually look at, you will see that there is this entire range, right? This entire range is there, and if you see right from the parent how the velocity profile was there, and when it actually for different from different, when you are at the lower stream, and if you are at the higher stream of what, the gradient which is there, the pressure gradient. So when the forward like favorable pressure gradient is there, and when the non-favorable pressure gradient is there. In two situations, there is the flow like this. So somewhere you are saying there is the flow reversal taking place, and somewhere there is the forward flow, like the flow which is actually taking place in the pipe flow with the one directional flow happening, right? And in this case, you can also see that the similar kind of fluctuation is happening, and the maxima is always towards the inner wall. In this case also, in this case also. So the reason, the most prone reason for the flow separation is actually forming where the low velocity is there towards the outer wall side. So the plaque formation will be happening there. So though these flow features which is explained over here, they are actually dictating some of the actual phenomena which is actually taking place, but in reality the flow is not like that. Rather, the flow is more chaotic. The flow is more chaotic. So like there will be this secondary flow which will be observed at the bifurcations, and because of that there will be separation of the flow will be occurring, leading to the plaque formation uh, at the later stage, and some cardiovascular situations will be forming. So this one I was saying is the important one, where this flow bifurcation is leading to the secondary flow, as we saw. So what is this secondary flow? Some flows which is so in order to actually characterize the secondary flows, you need to have three-dimensional analysis of the situation which is in hand. You cannot actually define this through the 2D analysis that mostly we numerically go for, or we actually analytically go for during our calculations in hemodynamics, right? So this chaotic motion which is happening, so you see it is actually not following an order flow like situation, like in the pipe flow it happens. So flow changes its direction at the bifurcation, at the moment where this divider was there, and then it acquires a secondary motion in the branch in which the fluid motion from the apex towards the outer wall, right? So from the apex towards the outer wall, there is this motion is happening. It acquires a secondary motion in the branch in which the fluid moves from the apex. Apex is this towards the outer wall, right? As the bifurcation angle becomes more blunt, okay, the strength of secondary flow actually increases. So if this increases, if this becomes more blunt, so it has to actually change its direction very much, and because of that there will be subsequent secondary flow forming, leading to the abrupt motion of hematocrits, WBC, RBC platelets, and obviously the associated peptides and proteins within the serum. So those are some of the important features. So in the lecture before this, we actually looked at what the relaxation time. So the relaxation time concept was very important. So like here it was explained that this Deborah number, right? So what the Deborah number says, that it's actually the main thing is that this DE actually is defined for this viscoelastic materials. So the viscoelastic material, so both because of the elastic characteristic, and they actually as in the elastic, once you deform them, they actually deform and then they regain their situation completely. In the viscous, it never regains its initial situation, and in the viscoelastic, it will regain its initial situation but not completely, right? So in that case, Professor Marcus Reiner from the Israel, he said that he explained it, and he introduced the Deborah number. So Deborah number came from the stating in the Bible, that stating says that the mountain flowed before the Lord, right? Means mountains which is there. Suppose Himalaya is there. So Himalayas also grows, and it formed. Everything flows. Everything is like fluid. But we are able to see if something is fluid within some time of observation, right? For example, God is here for long, if we know. So the Deborah knew two things. First, that the mountain flow as everything flows, right? So first thing is that you have to assume that the mountain flows, right? And then, but secondly, that they flowed before the Lord. Only God knows how it flows. That's why with different shapes and different curvatures, because of lots of aberrations which is taking place and the climatic condition, and because of lots of disasters which may be because of that the earth and the mountain formation happened. So that flows in front of God, Lord, and not before a man, for a simple reason. What is that reason? Man is in his short lifetime cannot see them flowing, right? But God is there. So while the time of observation of God is infinite, so he can see that. So the Deborah number is defined as time of relaxation to the time of observation, right? So lower the Deborah number means fluid like behavior is there, means lower the Deborah number means time of relaxation, time of observation is what? High. At the higher Deborah number, there will be solid like property, means uh, 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 if your time of observation is very small, okay, then D will be very high. So that if the time of observation, you are actually looking at something at micro scale, so you will not realize that whether the flow is happening or not, right? So it is that. So it's like high speed phenomena. So if you are actually observing a flow at high speed, uh, the time scale will be very small, and then in that case you may misinterpret that something is not flowing, right? So this was it for today's class. What I expect, the lecture has given you some insights along with some of the questions. Obviously, first lecture we had gone through video. First lecture was more theoretical, so I have not actually took more questions on that. But yes, that is self-explanatory, or some questions are there on that. And second, third lecture was a bit involved. It had some numerical concepts associated, so we have gone through that, right? And that was it for today's lecture. I hope everyone followed it. So thank you so much, everyone. Thank you. And let's wait for the next week. So next week will be last lecture. So mostly this pulsatile flow uh, uh, will be explained in the last lecture, and that is the main key. So entire sort of structure was built to reach to the main part of the course, which is the fourth week of the course, right? So you please look at it, you solve the assignments, go through the assignments, and if you have some questions, you please note that down and definitely ask in the next session, or if possible you can actually use the forum. So that was it. Thank you so much. Thank you, everyone.